Chapter 10, Lesson 4 is going to be about moving materials into, out of, and around a cell. Let's get into it. We have come a long way. We have introduced cell theory. We have learned what the parts of the cells are and what they do. And most recently, we have learned about the main compounds found in cells. Today's goal is going to be about how cells move substances that are created and substances that need to get into the cell. So cells can take in substances and cells can remove substances. Sometimes it's waste, sometimes it's something that is created by the cell and needs to be sent to a neighboring cell. You have had on your quiz questions which part of the cell decides what comes and goes. Hopefully, each and every time you mentioned the cell membrane. And the cell membrane is going to be very involved in today's discussion. So, to get through the membrane is going to depend on a number of variables or factors. It is going to depend on the size of the molecule. It is going to depend on the path taken through the membrane. And we'll see there's a few paths to get through the membrane. And then sometimes the cell needs to use energy and sometimes it's not. When you combine all of three of these variables, you can get several different ways to get through the membrane. Our job is to get it all straight. There are two main categories. The first is passive transport. The word passive that means does nothing. So in passive transport, the cell doesn't have to do anything. These are things that just already happen. So to get through the cell membrane without using energy is called passive transport. And passive transport can be broken down into a couple of subcategories called diffusion, osmosis, and facilitated diffusion. Let's go through each one of these and see what it looks like. The word diffuse means to spread out, which is something that we need all of you to do in the classroom, in the hallways, and out at recess. We got a social distance. We need you to diffuse. We need you to spread out. In a cell, this is done by using the already random movement of molecules, and that's going to take us from an area of high concentration to an area of low concentration. When teachers are mad at you because you're not social distancing, that's because you are very close together and you are very concentrated. You have a very high concentration of students next to each other. We need you to move to an area of lower concentration. In other words, we need you to move to where there's an area that doesn't have students. In a cell, when something diffuses, it's going to keep doing so until we have everything spread out as evenly as possible, and this is called equilibrium. Let's take a look at a couple of demonstrations of diffusion. So let me exit out of this and go to this tab. All right. So here we have materials inside some sort of container. It could be a cell. It could be a jar of water. It could be pretty much anything that's holding a substance. We learned way back in the first quarter that substances are always moving, particularly atoms. Atoms never sit still. Even in a solid, they are sitting and vibrating. Well, in a liquid, and cells are 2/3 water, that those particles are not sitting still. So when something enters the cell, things will diffuse on their own. These water molecules, as you can see, are just moving around, knocking into each other. And so when something is introduced, and I'll do it up here in the top left corner, every time the new molecule or new substances it interacts with a water molecule, it changes direction and moves out. And so as we watch this, the red particles are naturally, but very randomly, spreading out throughout this entire substance. Sometimes it goes back to an area of higher concentration where we've got a lot of them together, and other times they are spreading out towards areas of lower concentration. If we look over in the right side of the screen right now, that's an area of low concentration of red particles. But as we watch this, we can see that the diffusion, the random movement of particles, is causing them to randomly but eventually spread out towards areas of lower concentration. When it's all more or less even, like it kind of is now, we have something called equilibrium. Now, sometimes, let me exit out of this. All right. Sometimes there's membranes involved. So here we have a membrane, and it's got a pore size that will allow smaller particles to naturally diffuse through the membrane, but larger substances to not do that. Um, so the green ones, no matter how much random movement there is, they can never get across this membrane. But the blue particles, just by randomly moving, will occasionally shoot the gap and get in. And if we sat and watched this long enough, we would have an equal distribution of blue particles on both sides of the membrane. They will have diffused through the membrane naturally just because of the size of their particles, and we will have equilibrium throughout the entire thing of blue substances, but not the green. To bring back the tabs, just to bring back something that I forgot to talk about. Yeah, let's start the interactive. Okay, good. Now, before, when we were watching this, the random movement of particles is doing okay so far, but if we increase the temperature, we can get these substances to move a lot faster. We're giving them a lot more energy. And so diffusion will happen at a much higher rate. So I'm going to this time start it off we'll go to the bottom right corner, and we will start off with a very high concentration of the red particles. But because of the random interaction of all these other molecules, they will eventually move to an area of low concentration. So the low concentration now is on the left side, and these particles at a higher temperature will diffuse much faster. So temperature can really affect diffusion rates. Okay. Yep, we were almost already at equilibrium, and that happened a whole lot faster simply because we increased the temperature. All right, now let's close this for real and get back to our demonstration. Okay, our lesson. Okay, so that was diffusion. The second kind of passive transport is called osmosis, and this is when a very specific substance, water, is moving through the membrane. So when water moves through a membrane, we call that osmosis. Now, some membranes are permeable, and that means that pretty much anything can get through. Some membranes are semi-permeable, and only specific substances can get through. And kind of like when we saw before, when we had a membrane and the little blue particles could get through, but the green ones could not, that was a semi-permeable membrane. A non-permeable membrane is when basically nothing gets through. You will see the word osmosis in a lot of water filtration systems. If you look here on the box, under the label PureFlow, it says Premium TFC Reverse Osmosis Water Purification System. This is a water filter that works by it's called reverse osmosis, but either way, it's osmosis. It's water moving through a membrane. The filter will trap the things that you don't want to drink, and the water you do. All right. So when water moves across the membrane, it's usually happening because there is a concentration of another substance like salt or sugar or something like that, something dissolved in the water. And the cells really don't like it. In fact, nature just doesn't like it when things are out of balance. And so water will move through a membrane in order to dissolve the same ratio. So here we have this yellow line. This is our lipid bilayer. I told you that would be coming up again and again. So water molecules are eventually going to start moving through the lipid bilayer or membrane until there's an even amount of water on both sides. Okay, so when water goes through a membrane, that is called osmosis. Now, when water loves to do this is when we have an uneven amount um, of something dissolved. Um, so these red lines are the semi-permeable membrane. Water can get through, but the dissolved substance cannot. So if we look on the left side of this left beaker, um, on the left side of the red membrane, we can see that it looks like there's 1, 2, 3, 4, 5, 6, 7 of these particles. So we'll call it salt. Okay. So salt cannot get through the membrane, but water can. On the right side of the membrane in the left beaker, we can see there's much more salt than on the left side. And that means that, but the same amount of water. So the ratio of water to salt is uneven, and nature and cells in particular don't like that. So water is going to move through the membrane since salt can't, and water will move through the membrane until the ratio of water to salt is the same on both sides of the membrane. So if we look at the right beaker, there's an uneven amount of water. The water on the left side of the membrane is much lower, but notice we still have our 7 particles of salt. On the right side, we have the same amount of salt, but much more water, but the ratio of salt to water is the same on the left and right side of the membrane. All right. So water is when water moves through a membrane, it's called osmosis, and it will do that until the ratio of water and what's dissolved is the same. In this diagram, we can see that we have this is inside a potato cell, and these daisy-looking molecules are sucrose, which is a sugar, and the little dots are water molecules. Right now, there is a much higher concentration of sucrose molecules on the left side of the membrane than on the right. And so in this diagram, water will move from right to left until the ratio of water to sucrose is the same on both sides. The amount of water on both sides will be different, but the ratio of water to salt will be the same. So both diffusion and osmosis can move substances through a membrane. But to tell the difference, you have to look at what is moving. If water is moving, then that's called osmosis. If it's something besides water that's going through a membrane, that's called diffusion. All right. Our third type of passive transport is called facilitated diffusion. The word facilitate means to make something easier. So this is diffusion made easier by this cell. And this is because some molecules are so big that they need to be facilitated through the membrane. And so in the cell membrane are big gates called transport proteins. Transport proteins are in the cell membrane and they act as a double-doored gate. So here we have the lipid bilayer, that very recognizable double layer of lipids. And we have a substance that needs to get through, but it's too large to get through the cell membrane on its own. It cannot diffuse through a membrane. So the double-doored gate will open at one end, and if something that does belong enters the gate, then the first gate, the top end, will close and the bottom end will open, and the substance that the cell wants can enter the cell. If something that doesn't belong enters into the transport protein or the carrier protein, then the door just simply won't close and the bad substance cannot get in. And by having a double door gate, we're also keeping the things that the cell wants inside. So when you see these proteins called transport proteins or carrier proteins, these are to help molecules that are too big to diffuse through the cell membrane. But none of this requires energy, so it is a passive transport. Now, when something gets into a cell, it can actually take a couple of different methods. So to get into the cell, past the cell membrane, a substance would have to use one method like osmosis or facilitated diffusion. And then once inside the cell, then it can actually just use regular diffusion to spread out. All right. Active transport is the opposite of passive transport, and that means that it is when you don't want equilibrium. The cell actually wants an uneven amount of a substance, and it wants a high concentration of a substance. Now, because this is fighting what happens naturally, that's going to require energy. In diagrams, you'll often see the molecule ATP. Stands for adenosine triphosphate, which nobody ever says. We just say ATP. So ATP is an energy molecule. It's made by the mitochondria. So in active transport, we are going to require energy. So in a diagram, we can see on the left, diffusion and facilitated diffusion. These are passive transports. There's no energy icon. Over here on the right side, we can see this ATP sign, and that means that energy is being used, and so that is an active transport. Active transport, as we mentioned earlier, is when you want to reverse the flow and you want to have a high concentration. So starting at the top of this diagram, we can see the lipid bilayer. Diffusion is when a substance naturally goes from an area of high concentration to an area of low concentration, and it goes through the cell membrane on its own. Facilitated diffusion will also go from an area of high concentration to a low concentration, and we can see that there's more of these triangles on the left side than on the right side, and so the triangles are going to move to where there's fewer triangles. On the bottom side, we notice that there's only two of these green squares, and on the right side, there's a lot of green squares, but the cell wants all the green squares. It doesn't want to balance. It wants them all. It's greedy. So it is going to require energy to do that. So here we have our ATP symbol indicating that energy is being used to move the green squares from an area of low concentration to an area of high concentration. That is active transport. Every now and again, the cell has to move something that's too big even for the transport proteins. So it actually has to use an entire section of the cell membrane. So the cell membrane, in order to do this, will form a pocket and wrap around the large substance. And then once it has it completely encircled, it will pinch off, and then we call that a vesicle. So at the top of the screen, we have something trying to enter the cell. And so a pocket forms in the lipid bilayer. It completely surrounds and then pinches off and then enters the cell as a vesicle that's carrying the substance. The cells can also use this to have a very large substance exit the cell. So the vesicle will merge with the cell membrane because they're both lipid bilayers, so it's easy to merge. And then it will just kind of flatten out, and the substance can now leave the cell. So these have two fancy terms that we have to keep straight. When a cell is using the entire membrane to take in a substance, that is called endocytosis. And when a cell is using this technique to remove a substance, that is called exocytosis. And the way that I always remember it, endo sounds like enter. And so endocytosis is entering the cell, enter. And exo is like exit, it's leaving. And so exocytosis is exiting the cell. So endo enter, exo exit. So good, the GIF worked. So here we have some substances that need to enter the cell. So the whole cell membrane will form a pocket and then pinch off and then become a vesicle. So here we have these particles that want to enter. The pocket forms, it surrounds it, and then it pinches off, and now you've got a vesicle carrying the substance inside the cell. One more time, and then I'll move on. Whee! Okay, so your job is to read pages 356 to 361, answer all the questions. Good luck to you.